Welcome to MedStartr Momentum 2016. My name is Alex Fair. I'm one of your hosts. Also hosting is Ben Choder over by the camera. Raise your hand, Ben. And Tom Tagarillo up in the front. There's lots of other folks here from MedStartr, from our sponsors. So NJIT, Moses Singer, and our lead sponsor is DataArt, which made all of this possible. So thank you. In the back, Dan from DataArt. Let's a big round of applause for Dan and DataArt. Thanks, guys, for making this happen. So, but you don't know what's going to happen yet, right? So we've got 70 different speakers and panelists. We've got 15 companies coming and pitching, telling you about their great new innovations for healthcare. We've got over 170 people registered, although you can't really tell at this point because I guess it's early on a Monday morning. We've got a very packed schedule today, which I put up on the screen here. It's also in your programs. We have actually a very tight schedule, even though we're starting a little late. It's every 10 or 15 minutes, we'll be changing what's going on stage and a lot of really exciting stuff. So there's a lot of members of the walking gallery here. So if you see these jackets that look like this, essentially ask the people what their story is about because they're always very interesting. And actually, that's an important point. You guys are all extremely interesting folks for healthcare innovation. If I could count, I would run out of fingers and toes to find all the amazing people that have helped me with my various different endeavors and startups and things like that. So flashing on the screen are the different panels and things like that we have going on. But the first speaker of the day is a guy, Dr. Siddiqui. He's famous for having created lots of amazing stuff. We can pull up his deck, please. So the Xbox Kinect and those things at Dwayne Reed and CVS that you put your arm into that takes your heart rate and your temperature and your blood pressure. So really amazing guy. I've seen him speak before. I'm really excited to hear him speak today. So everybody will take your seats, grab your coffee, something good to eat. Let's get this program started. Mark, can we cue up his deck? Okay, without further ado, here's Dr. Siddiqui.
Good morning. I'm sure everybody can hear me. Early morning start. First, a confession. Alex, I actually forgot that I'm speaking here. So I had committed to some other speaking engagement in Chicago at the same time. So I had to move that to next day so that I can, once Alex called me like, hey, where's your talk? It's like, oops. Anyway. All right, let's get started. I usually don't let people put in Kinect in their stuff because just kind of breaks the way I bring out what I'm talking about. But anyway, Alex did a little bit on the title himself. So I'll quickly start what I do. I'm co-founder and CTO of a company called Higi. I was the founding CEO. We started about 4.5 years ago. Let's see if it works. So quickly talk about a little bit about Higi is, then talk about a little bit of my background, so give you some context on what I've done and why I've done some things, and then really one of the things I talk about really is how do ideas evolve, and give you an example of Kinect and how all that started. Higi really started as a consumer health engagement platform. The idea was to empower the consumer to know their numbers, because that's a lot of the research showing that the more you know, that was one of the motivators to lead habit formation and change, as well as then provide, using that engagement solutions, products in a B2B space to payers, health systems, pharma, and things like that. So we started in 2012 with the focus on building a engagement platform with a twist that it has a hardware component with the kiosk and retail locations nationwide, mostly in grocery and retail pharma. So in 4 years, we are now in about 11,000 retail locations nationwide. We are within 5 miles of 78% of US population. We do about 5 million screenings a week, done over 100 and what I think now the number is 185 million. We also connect to all of other wearables, home monitoring devices, more than 70 of them right now. We have 35 million people who've used the station nationwide. Some of the big customers that we have in the retail space, and down below on the slide. So the first three and a half years, we really focused on building this network, because without this, providing convenient free access to basic screening, where we do cardiovascular screening with hypertension, arrhythmia, things like that, as well as diabetic screening through surveys and obesity screening. So without this, really didn't really make us a compelling argument for any health system or payer to take us seriously. So since then, we've launched our health solutions products to really understand the risk of population you are trying to take on with this capitated market or contracted relationship building with payers and employers, as well as population screening solution, employee wellness solution, things like that. So anyway, enough about Higi. My background is that I started a long time ago as a software hack, built my first software in the 80s. It was an education system before Windows days to do full-blown education, exam management, scheduling, things like that. Sold that company a long time ago to another education software startup out of Singapore. And this was in Pakistan, not in the US in the 80s, so way ahead of a lot of the stuff happening. After that, decided to go to med school. And being the only medical student in Pakistan who knows how to actually code, it gives you a very interesting relationship with your faculty and everybody else. This med school was the first one to put an EMR in 1990 in Pakistan. It was a Meditech system. They used a proprietary Unix-based language called Magic, if some people remember that. It was based on a MUMPS database. So learned a lot, and being the only person who knew how to do some of the stuff and understand the clinical side of things, started doing data mining. So started my first data mining project in 92 to understand how do we extract data and how do you analyze it to risk assess, identify risk of population, do economic trends and what is costing it, understand prediction models for nosocomial infection. So this is way ahead of a lot of things we think about. So, but got me very familiar with MUMPS, and you can imagine what happens next. So I came to NYU, trained here. In my first rotation, I was put in as an intern at the VA, but had just converted to the CPRS and Vista EMR. Well, guess what? That's also based on a MUMPS database. So being the only intern and resident who actually knew how to query and mine, that gave me another interesting opportunity to do some innovative stuff here at NYU from a data mining point of view. Finished my training here and moved to Geisinger Health System. And Geisinger decided to put, they were moving. Glenn Steele had just joined. They were going away from their fee-for-service to quality-based care, what they're known for right now. And we were trying to look for what do we do from an EMR implementation point of view. So we decided that, the RFP we sent out in the 90s, nobody could respond. So we decided to let's find somebody, some new, smaller startup-y or smaller EMR vendor that we can convince to change based on what we want to do. And we found a company with a small 4-letter acronym in Milwaukee called Epic. Funded it and did one of the early implementations of it. And guess what? That's also based on MUMPS. So suddenly being the only physician in the team who actually knew what to do with that gave me a little bit of edge and did a lot of interesting things over there. Moved to Baltimore VA, as well as University of Maryland, and joined there as a CMIO and build the imaging informatics training program and fellowship to really build a multidisciplinary approach to software development. This is where I really switched back from my clinical work to more on health IT and more on software development side of things. So one of the things we realized was that working with industry, it becomes really hard where universities are trying to push stuff out. I mean, we just talked about it earlier, about this concept. So we decided, why not us take on some development aspects that vendors are trying to do but having a hard time figuring out because they don't have access to data, they don't have access to understanding of clinical knowledge. Here we have all this mindset. So we built a full stack development shop at University of Maryland and did contractual work for Philips, Siemens, GE, you name it. And out of that, we also launched a bunch of different startups. Some were successful tech transfers, some successful launches, tons and tons of failures. But that was the mantra, like, try anything you can, fail fast, and move on. So a bunch of different things came out of that. Um, One of the ones that I led was a semantic analytics of search engine processing. So nothing to do with healthcare. We were trying to understand how do you understand semantics of a web page. So when a web crawler goes and downloads all the content from a search indexing point of view, how do you post-process that index to understand what did you actually capture the data for? We licensed this to Google, Yahoo, Microsoft, everybody else, and got acquired. That landed me, at the same time, I'd moved from Maryland to Johns Hopkins and to build the Center of Technology Innovation to do the same thing that we did at Maryland over at Hopkins. After the acquisition of that Yada Look thing, I landed in Microsoft. I was brought into really, physician in a software engineering company. It's with not really having a degree in software engineering. It's a very weird position. So like, let's make you do all the strategy work. You're a radiologist, so let's do medical imaging. Within 3 months, I took over engineering execution of the medical imaging team, and then eventually all of the platform engineering team. So build the whole data warehouse product, used to be called Amalga, that Microsoft had, all the back-end systems. So funny thing, I was a physician running back-end platform development for Microsoft for these health solutions. My last year at Microsoft, the personal health record became my problem called Health Vault, and it got me interested in consumer engagement. What I realized immediately was that we built great technology, but we hoped that the partners will bring all the consumers and the patients to the platform. And all the partners thought, hey, Microsoft has so many users on Hotmail and Xbox Live, they'll bring all these users, let's go partner with them. So nobody focused on consumers or the patients, everybody focused on building technology, and it was pretty horrible. We did a lot of experiments to see how we will actually change that stuff. But Balmer decided to exit out of this space take the whole group as a joint venture with GE to form a company called Paradigm, which now GE brought back into their portfolio. So I left Microsoft to start Higi. So let me switch gears here into the whole idea of what my talk is supposed to be about. So if you think about how do ideas evolve, right? Everybody likes to compress when they say like, hey, I had this eureka moment, I was in the shower and suddenly, voila, here's the magic and I came with this idea and here you go. But if you think about it, it really doesn't happen that way. That idea has been probably sitting in your brain as a slow hunch over time, over decades, over months, over years. And usually it's not just one person. It's somebody else's hunches, and the people in your network, people you interact on a daily basis, they have slight hunches going on, and eventually they all coalesce together over a long period of time to really become the eureka idea that you're talking about. If you go think back things you're doing, like how did it evolve? What was your thought process behind it? So for me, one of the things I was trying to figure out is, in this whole journey of building my software skills and things like that, one of the early things I used to get frustrated about in med school when doing data mining was I could mine all the structured data. There was a lot of issues with unstructured data, but also all the images. Being interested in radiology is like, how do you really understand what's inside the image? I mean, there's so much information here. Am I really relying on radiologist's report to figure out what it is? How do I know? Not only that, but how do I represent data on images? So GPS was just coming out, and the idea was, how do we actually represent the similar kind of data in healthcare into imagery the way GPS has changed it? So let me take that story now. So how these ideas on Kinect and stuff go back to October 7th, 1957. Sputnik is launched by Russia. So when they launched Sputnik, they had made sure that people don't think it's a hoax. So it actually broadcasted a signal at 1 kilohertz range. So people can actually track and listen to the beep, beep, beep sound that happens. So this happened over the weekend, and October 9th, Bill Geyer and Weifenbach, both were young researchers at APL lab in Johns Hopkins, Applied Physics Labs in Laurel, Maryland, and they were sitting at cafeteria talking about, wow, this is such a great thing. First ever man-made satellite is in the, in the orbit. And they were thinking about, has anybody even tried to figure out, listen to this signal that they're talking about? And Weifenbach was doing his PhD in microwaves, and he had a 20 megahertz antenna sitting in his office, which he was using for his purposes. So they left lunch to see if they can figure out and listen to this orbiting satellite. And within an hour, they were able to crack the lock on the signal. And then, as the word got around, other people started to come up to their office to listen to this beep, beep, beep signal, and they realized that this is a historic moment, we should be recording this thing. So they record the audio and put timestamps to every time a beep happens. And what they noticed is that the variation of frequency was changing slightly during the day. The Sputnik was orbiting every 96 minutes across the globe, and there was this fluctuation that was happening, and they realized this is probably frequency shift because of Doppler effect. Like, can we figure out the speed of this thing? So they started doing a Doppler curve to see what is the speed of this thing based on the frequency shift that is happening in the signal. And that led to them figuring out, and within like a few days, they had the entire orbit of Sputnik accurately mapped out from just one known location on the ground. So the guy in the middle, their boss who ran the APL lab at that time, called them in their office, is like, could you do this thing other way around? Could you actually identify a location on the ground with a known location in the sky? So they were known location in the ground, and they're trying to look for something unknown orbiting the Earth, but what if you reversed it? You had orbiting things in the sky, but a known location on the ground was not known. And they thought about it, and it's like, that would be probably slightly easier to do. So why don't you go work on this problem and come back? And they came back in a week, and that led to genesis of the initial transit system that became GPS. So the problem he was trying to solve that he didn't tell Guy and Weifenbach at the time was that the US was building our submarine-based ballistic missile technology, and the problem they had that from Pacific Ocean, if you want to target Moscow or some other city, how do you actually know where the submarine is accurately? And that's what the initial implementation of this was. But they never envisioned what GPS will do, from identifying submarines in this to identifying the nearest cappuccino I want to go grab, right? So how has GPS changed our lives? It has changed how we look at traffic data. You just imagine making a decision on your route based on Excel spreadsheet that tells you every single street, every single block, and what the speeds are, and then trying to figure out what route I want to take. It's just impossible. You just can't compute that kind of information in your brain unless it's shown you visually. Same thing with weather data. Same thing with finding your nearest cappuccino. But guess how do we look at our healthcare data today? Still spreadsheets, right? And we have gigantic list of labs and values without really understanding the context of what organ system is it affecting, what really is happening to it. So there's no context that imagery brings it to bring the data and the representation part of, representing into a human body, and it gives you different insights. So this idea kind of started in my brain in 92, 93 timeframe, like how do you actually do this stuff? And I had no idea at the time how to do it. Slowly kind of evolved. So when it came to University of Maryland, one of the early things that we were trying to figure out from a quality point of view is that how do we accurately know which scan this is? Like text would say this scan was done for a CT chest or CT abdomen, but how do you actually know it actually was that? And a lot of time there was mislabeling of the imaging. So we started initially as a quality project to see if you can classify a CT scan into, is it a neck, is it a chest, is it abdomen or pelvis, and then correlate to how actually the technologists who were classifying these scans were doing it. But soon we realized, as digital imaging was evolving, the PACS systems were coming in, and there was research coming out that to look at different diseases or different anatomic structures, you had to have different types of image presentation on the monitors. Right? Some you need to look at an axial plane, like lung nodule. Lung cancer is much higher accuracy or much higher sensitivity from radiology detection if you look at it in coronal plane in what is called minimally invasive projection views. So these are and then what we started to see is that our residents and junior attendings had a hard time remembering what is the best, most optimal way to set up these settings to look at these images, because now it was no longer film, right? Now these were digital images. You could manipulate them however you want to manipulate, but what is the most accurate way to do it? So we said, hey, can we take these basic understanding of what is this image part of abdomen, chest, pelvis, and actually auto-create these hanging protocols, that how is the image shown based on what you just opened, what is inside the image. So even if the study was done as chest, but you scroll down and they've captured the abdomen, how do the settings automatically change to that stuff? So really started with understanding of just, is this image in a chest, abdomen, and pelvis? From there, it kind of moved on to much more finer structures. What are the things that are hard for physicians or radiologists to detect and are really bad at detecting, but are common problems? So meniscal tears are one of these issues, and cartilage injury of knees, one of these issues, that these are 2 millimeter, 3 millimeter structures, and you're looking for a tiny little gray signal inside it. And it's unless you're a specialized musculoskeletal radiologist, practiced for more than 10 years, your accuracy is not that great. So we worked on seek if we can automate recognition of the knee and then on MR imaging and then be able to recognize these injuries automatically. So we did macro level recognition to micro level recognition to understand what is happening in an automated manner. This is where the whole idea of machine learning, and I remember trying to train for this knee thing, we would run the training algorithm for like 2 weeks because processing power wasn't there. The GPUs weren't, NVIDIA wasn't doing their deep learning GPUs to be able to do all this stuff. So you're running, farms of CPU machines running at 100% capacity over a week, heating everything up. We went to a nice and toasty research lab, and this was happening. So when I reached Microsoft, this idea was that let's invest more in understanding, can we recognize human anatomy automatically on medical images? And a lot of the interest started with, there was 2 guys on my lab who were arguing, do we do CPU and GPU? At that time, there was no GPU-based deep learning systems. NVIDIA had just come out with a Tesla card for higher GPU rendering. And because being in imaging, we were using those cards to do 3D rendering. And these 2 of my team members and Microsoft would always fight which is better, CPU or GPU. So we did a bake-off. And the CPU guys won because they would just put in more PCs and make it work faster. So the GPU guys asked me if he wanted to take a month of sabbatical to do this GPU optimization. So he went back and rewrote the entire 3D processing codec in assembly to remove all the noise behind it and made it 200 times faster than CPU. That became part of the CUDA codec that now NVIDIA and everybody uses for deep learning purposes. So that became now our understanding on how do you actually do deep learning on GPU started. So we work with NVIDIA to really figure out how to do deep learning on these GPUs. And this is from 2008, 2009 timeframe. So this is like way ahead of everybody else trying to do this deep learning on GPUs. And then again, another thing was that when we went to this concept of recognizing human anatomic structures on medical images, everybody's like, why do you want to know where the heart is? We know where the heart is. You can listen to it. Why would a doctor care? It's like, it's not about the doctor. It's about the machine. Like, oh, we need to figure out segmentation. It's so hard to segment. All organs are so different. It's like, no. We don't care about segmentation. We just want to know, is this image have a kidney or not? Yes or no answer. I don't care how it is. So that kind of dumbed down the problem to, is there a bounding box? In this bounding box, does this organ exist or not? So that was the idea of ignore segmentation, ignore specificity, just need to know yes and no answer. And that started the whole iterative process of, okay, fine, we just need to create multiple nodes that say yes, no, if the organ's in this box or not. So that's what we were trying to go through. As you know, in trying to do anything medical imaging, you need to do a lot of research and prove all this out, and we were going through this route to validate clinically and get through FDA. In the meantime, and this is 2009, I get a call from Xbox one day. It's like, hey, what are you guys doing? I heard you're doing image recognition. It's like, yeah, we have some images. Can you guys recognize these? I was like, what are they? It's like, it's a monochrome images, just like X-rays. Can you look at them? So it's like, okay, so like, how would you segment this? So it's a human figure in grayscale, so I segmented around 13 body parts. I was like, can I give you some, and can you guys run your algorithm, see if you recognize it? It's like, sure. So in 2 weeks, my team worked on it and showed him, here it is. Like, what is this? Like, no, it's just nothing, we're experimenting. We had no idea what it was. So we built all the stuff, and then we got called in a room locked doors, a lot of lawyers had to sign this thick NDAs. Then we kind of found out what exactly this was that they were working on. So the idea of using human body to game as a game user interface started a while back, but and they were trying to figure out what tools, techniques to use, and then our team figured out how to use machine learning and deep learning to do image recognition of body parts. That's what ended up going to the foundation of algorithms that ended up leading to Xbox Kinect. So this is the early model that we did on recognition of human body and different body parts live as this is happening. Which led to this. So I didn't come up with the idea of Kinect or anything like that. It's just that we worked on the recognition portion of it and optimized the algorithms to do it much more accurately. But if you think about it, right, so if you think about all the slow hunches that were happening over time, a lot of different people on my team, a lot of different people in different groups, different problems, slowly culminating towards solving iteratively each of them to get to this stage. So what did we do with this beyond Kinect? So actually, a few more things in Kinect. So obviously, as I explained, how do you do machine learning on GPUs was one of the early works that my team did at Microsoft. The other one was that once you realize that you leave any kind of clinical institution, you don't have access to health data anymore. So I had access to 50 CAT scans, and that's it. So how do you now train where our training algorithm required 500,000 CT scans to train for each organ? How do you get those? At Hopkins, we used to do 180,000 across all 9 hospitals a year. This is like 3 times Hopkins data sets for the whole year that I needed to train just for simple organ recognition. And then one of my researchers goes like, there's this group sitting next to me, they do synthetic imagery for movie industry. They create all these realistic hundreds of thousands of people for movie that are all randomly generated. Why don't you talk to them? It's like, no, synthetic stuff doesn't work. It'll create noise and you'll only train on all the artificial stuff that they're putting in. It's like, well, what's the harm? My whole idea of, fail fast, like, let's just do it. Why not? It's like, here's 50 scans. Here's the variability of organ tables from anatomic textbooks on how these organs vary. Can you create synthetic images? So 2 weeks later, one of the researchers sends me like, here are 2 data sets. One is real, one is synthetic. You as a radiologist, can you tell me which one's which? And I just could not tell. I was like, I cannot tell as a human that which one is the synthetic scan, which one is not. So they generated 500,000 synthetic CT scans for us to train. And guess what? There was no issue of artifact learning. That's how it ended up being. Anyway, so we implemented the same thing as in our kiosk, where somebody stands in front of it. It recognizes your height, what mood you're in, some of the other analytics beyond that. This gave us better understanding on machine learning and deep learning to apply on other imagery. And one of the applications we are currently building is recognizing food in images. It's still only at 70% accuracy, so we haven't gone public with that yet, but this is a works in progress, and eventually we'll go. I think I'm going to end. My time's up. Thank you.